move around a lot, so I apologize if I'm a little bit too animated. I actually decided to take this microphone instead of using that microphone, so I kind of like to jump around. So I'll just go ahead and dive in. War texting is a really interesting topic because it's about something that a lot of us don't really know about yet, which is machine-to-machine. Okay? So I'll describe what machine-to-machine is all about and kind of give you an introduction about why it's interesting from a security perspective. And I'll talk about some devices that I've actually compromised successfully in machine-to-machine. But first, of course, I have to do the obligatory, like, who am I and why am I here and all the other good stuff. First, I feel extremely blessed to be invited to come speak here. So thank you so much for inviting me to go. And on behalf of the filelcon organizers, I'd just like to say thank you to all of them and everyone for having me here. It's a great experience. As far as who I am, my name is Don A. Bailey, and I'm a research director at ISEC Partners Incorporated, an organization now owned by NCC Group, based out of the UK. So we're primarily United States consultants, but we do specialize in computer security, everything from Web 2.0 to SMS security to hardware security, pretty much everything in the middle. We try to do a little bit of everything. So ISEC Partners, like I said, is a worldwide organization based with NCC Group, and they're really not all that interesting, which is why I'm only going here. So we'll just go ahead and skip talking about them and get down to the actual brass tacks. This is machine-to-machine, okay? This is the reason why I'm here. It's like this. And you might be asking yourself, what is that? It looks like a pill bottle. It is a pill bottle. It's a very interesting pill bottle. It's a pill bottle that has been enabled with cellular technology, okay? And it's genius, it's brilliant. So essentially what occurs is every time you take off the cap of the pill bottle, it sends a message to a server saying you have taken off the pill, right? And it assumes that every time you take off the cap, that equates to you taking one pill, or whatever your prescription is. And that's extremely interesting because now people can take tally of what you're taking, how much you're taking, when you're taking it, etc. So that seems like probably a privacy problem. And we probably all want to get a little bit more, or take a little bit more control of our privacy. And we don't like it when things get leaked, right? And this presents a really interesting security problem. But there are a lot of benefits here, right? Which is the reason why this exists as a product. If you think of your elderly grandparents or somebody in your family that has problems with their health, this technology can really help them and help you facilitate their health and lifestyle they may not be able to take, right? And that's a beautiful thing. That's a really beautiful thing. Technology shouldn't, scare us as much as it enables us to have better lives. But it comes as a cost, a really severe cost. And that's the evolution of devices, security, and the world that we live in, right? Machine-to-machine is a huge step forward in this evolutionary process. And this is pretty much the evolution here, right? The old mainframes, the PDPs that we used to see, huge craze in rooms, enormous amount of space. And today, we essentially have a mainframe, or what used to be a mainframe, sitting in our phones. That's a huge evolutionary jump for mankind. It's significantly important. But what's extremely interesting about that is the changes in security between here and here, right? Obviously, the first systems that you saw in those giant rooms full of computers weren't interconnected. And if they were interconnected, very few people had access, right? Dr. Bajaj mentioned several times this morning that it's all about the interconnectivity of systems and how that information can be accessed by other parties. Today we have that incredibly, more well-connected world than we ever thought that we would in just the mobile device. And it's moved from the mobile phone into the legacy engineering technology that we used to take for granted, which is everything will be a computer, right? Not just your phone, but everything around you is going to be enabled in some fashion. Your medical devices, your car, your home, all kinds of industrial security systems, right? Even these cameras that we see in this talk here, will very soon be cellular connected in some fashion, right? And there are even people like CNN, for example, actually has video cameras in the field that are attached to satellite units that use machine-to-machine technology to upload those streams through satellites to CNN Central in New York, I believe. That's exceptional technology, but of course, again, it's the evolution of security along with that, right? And there are a lot of different things that I could have compromised in M2M, and I could have been ATM machines, as we know that's a very popular target. Of course, Barnaby Jack got there first in 2010, and he did an exceptional job. Now, granted, he didn't do it from the cellular network, but he got there anyway, so I figured, all right, it's already been done. That's not fun anymore. So what we're going to do is we're going to talk about the evolution of breaking M2M, okay? And there are three very important parts to breaking M2M. And what's amusing about that is I chose none of them, okay? But they're still very important to discuss, because this is where the technology and the state of the art in breaking M2M is going to go in the near future. Today it's not so relevant, but I'm here to tell you why. Primarily, we have these three technological issues or challenges. The first one, of course, firmware over the air, and we'll go into that. So what is firmware over the air? Anybody? Anybody want to yell something out, what this is? So this is basically, you have a firmware upgrade that needs to occur in the field, right? And that's whether it's your phone, your iOS operating system wants to auto-update, or it's, the ATM system that needs a firmware update to make sure that it doesn't dispense money to the wrong person, right? An OTA update is an over-the-air firmware update that's sent through the cellular network. Now, nobody's receiving that update except for the machine. It's an unmanned upgrade. So you're thinking, wait a second, nobody's actually there to implement it. That's going to have huge, huge consequences if it's done incorrectly. That's correct. Problems with firmware over the air that the GSM Association and other associations have not yet been able to create a concrete standard. So there is no actual standard today for firmware over the air. Okay? And that's really important, because if we're going to break it or try to protect it, we have to have some kind of a structure. We need to understand what are the methodologies, what are the technologies, what are the strategies involved in deploying this, right? And if you can't concretely say what those things are, then you have no path for breaking or implementing security for this technology. Okay? So to me, firmware over the air is an exceptional advance in mobile security and mobile technology as a whole. But the problem is you'll see it implemented in all different kinds of ways, right? Since there is no specification. One perfect example that I'll show you later, I hacked a car. How did I hack the car? I broke firmware over the air. Okay? But that was only one of the ways that I actually attacked the car. There were several ways, and there was a more significant and more successful way that I actually is the one that I demonstrated. So there are a lot of negatives, and the conclusion for firmware over the air is, while it's really interesting academically, it's meh. I have absolutely no motivation to investigate this whatsoever. Okay? It's silly. It's cool at a later time, but right now it's silly. There's no reason to do it, right? I have no motivation. So the second primary technology in attacking M2M is the baseband chip. And how many people are here are very familiar with attacking basebands or attacking GSM systems? Anybody throw a hand up if you're very familiar with that. 1 minute. A couple. All right. Awesome. So essentially what occurs here is everybody has a baseband module, okay? In your phone, the cellular chip that talks to the base station or the carrier's network, right? It's just a small little microcontroller. And all that microcontroller does is manage the radio frequency. And the radio frequency itself is controlled by software that runs in a real-time operating system. And it runs at a high priority amount of code that can't be a large amount of code, because RF is lossy, right? If the link becomes unstable because you're running too much code, it's going to drop your call. So the amount of code that's actually being ran is very small, which also means that the security measures that are taken in that code, very few, right? Which also means if you are running a baseband on C, C++ technology, as opposed to Java, you are more likely to be able to compromise that phone over the baseband than the actual application. Because there are no security technologies in place, there's no address space layout randomization, there's no non-execute, right? There are no bits such as that. It's all just an embedded real-time operating system that's very easy to manipulate. You can trick it, right? Just change some of the GSM frames, adjust a couple of integers, maybe you get a buffer overflow. Several individuals, including the Grug and Ralph Wyman, have done exceptional over the baseband channel by manipulating GSM frames. Now what's interesting about that is it's a localized attack. If I want to attack your GSM baseband, I have to be in range of it, right? Because it's RF. I can't be on the other side of the world. I have to be next to your phone, implementing my own base station and manipulating those frames. That was previously. Now we know that baseband is no longer local. Baseband attacks can be performed over TCP/IP. Because now in machine-to-machine security, basebands have TCP/IP stacks embedded in them. And why do they have that? Well, most of these technologies that are now cellularly enabled, like ATM systems or point-of-sale systems, they have very small application footprints, which means that they're using very small microprocessors, right? And those microprocessors don't have enough robustness or power to have their own TCP/IP stacks. In most cases, these aren't even running Linux. It's some kind of proprietary baked operating system on their own, right? So they rely on the baseband to connect to the internet through the cellular channel. So now what I know is, I know the baseband has TCP/IP embedded in it, but it's still the same old operating system that can be manipulated if I throw bad GSM frames at it. Which means, do you think that's going to be any better or worse code running a full TCP/IP stack? Processing HTTP, FTP, DNS?
Worse.
Worse. Way, way worse. Okay? That's the reason why this is an exceptional avenue for remote exploitation of M2M. Okay? It's very elegant because it's going to be chip specific, but it's going to be you attacking one large deployment of chips. The problem with firmware over the air is firmware over the air is implemented by the application developer as well as the cellular carrier, which means they can come up with any combination that they want to of how to implement firmware over the air. The baseband TCP/IP stack is implemented by the vendor. So if you're AnyData, uBlocks, Centurion, or any of the other major baseband manufacturers, they're going to implement one TCP/IP stack and deploy that on most of their chips. So if you find one vulnerability, it's very likely that you're going to get mass compromise on all different kinds of chips across their entire engineering line. That is exceptional work. The problem is that it's extremely difficult to debug. Most of these operating systems are closed. You have to reverse engineer the entire operating system, right? That's a very significant time commitment. And we don't have time for that, right? We have other things to do, like hang out in Goa, right? So we don't really want to waste our time. And I kind of think like, okay, this is exceptional long-term research, but if I want to go hacking a building or a car or an ATM today, probably not so much. So the conclusion for this is it's kind of like having a shark with a laser on its head. I've always wanted a shark with a laser on its head, but the fact is I'm just never going to get one, right? Not going to happen. So it's a cool toy to have at some point in the future, but not now. And the last of the three technologies is APNs. So if you're not familiar, APN is essentially a private network, right? But this private network is isolated. It's an isolated network within the specific vendor and their specific application. Okay? So if I have an ATM machine and it's a globally accessible, cellular-enabled ATM machine, it's going to connect to the cellular network with an APN. It's kind of like a VPN, but for the cellular network, right? So it connects to its individual APN, and the only other thing that's supposed to be on that network are other ATM machines of that manufacturer's nature. Right? And they all connect to some back-end server that uplinks to a bank and then routes the information back and forth. It's supposed to be entirely localized. But, of course, the issue here is that there are a lot of tricks towards accessing an APN. In fact, you guys may be familiar, it was 2 years ago, I believe, in South Africa, when people actually started breaking open traffic lights. Anybody hear about that? Yeah. And what were they doing? They were stealing SIM cards, right? And the reason why? Because they knew that if they took the SIM card out of the traffic light and threw them in a mobile phone, they could start making free phone calls and free SMS. What's actually occurring is they're connecting to the APN defined for the traffic light, programming it into their phone, and then using that to connect to the world, making and receiving calls. Okay? So people started to get smart and realize, wait a second, we have to tie down the APN. So they figured out how to, create this PDP context so they can tell what kind of device is connecting. If it's a phone, don't let it in. If it's a different kind of device, let it in. But the thing with APN attacks is that you're basically joining a VPN. You're connected to an IP network, in which case you're not really attacking M2M anymore, right? You're attacking a network, a computer network. And that's not the point of M2M. The point of M2M is to attack the actual implementation, not the network it's connected to. If I own an APN, I might as well be owning the internet, right? It's just another piece, a network somewhere on the internet. So there's no reason for us to talk about that. That's completely uninteresting. There are some actual interesting facts there with APNs, but you don't really need to know anything further. So, the number one way to actually attack M2M today is by taking a poll of all the successful M2M implementations that are in the field and basically just reverse engineering them and seeing what the fingerprints are, right? What are the commonalities and how can those commonalities be abused? This is a very simple example of an extremely commonly deployed M2M system for microchip. Very simple, very cheap. As you can see, there's a GPS module in the top left, right? That's your GPS antenna. There's a little supporting chip in the bottom left that drives GPS, and then there's a U-Blocks in the center, and that U-Blocks is the baseband chip. Okay? On the other side of this PCB is a microchip PIC32 microprocessor, right? What's very important to notice about this picture is that three things are here, okay? GPS module, GSM module, or some kind of microcontroller. You'll note that the microcontroller, especially a PIC32, not going to be running TCP/IP. It's a very low power, low cost, low speed processor, right? The U-Blocks, on the other hand, does enable TCP/IP. And this guy is what's going to be connecting everyone to the internet. So this is a very common module that's dropped into legacy engineering applications to throw any old legacy engineering product online. Okay? So, those commonalities are what we look at, those three primary modules. And what's really important here is that the baseband must be approved by the specific vendor, okay? So if you're AT&T, or you're T-Mobile, or you're Sonet, or whomever, you're going to have a public list of what baseband modules are approved or pre-approved to join your network. So somebody can't just, come up with some GSM module, throw it on a board, and then connect to AT&T. That can happen because there are certain regulations that need to be passed to ensure that that device isn't going to be bleeding into our spectrum, isn't going to be interfering or accidentally jamming other devices around it. And in certain cases, as I believe somebody is going to talk about later today, M2M is used within SCADA and other power systems, right? So you don't want bleed out from these products to affect engineering technologies that are controlling critical systems in and around the M2M network, right? So if the list is approved and made public, we can easily go through that list and determine which chips are more vulnerable than other chips. And I'll talk about specifics and how later, because they're very, this chip, completely ownable. And not only is it completely ownable, I don't even have to do anything. And these 50 different vendors implement this chip in their products. That's a huge danger. And I guess I should note, the microcontrollers, if a lot of people aren't familiar, they're so small and so inefficient for actual modern processing that they have typically around 4 kilobytes of RAM, right? Not a lot of RAM. They only have about 128 kilobytes of code. Flash, right? Not a lot of flash. Can't do a lot of robust security with those kinds of microcontrollers. So, the communication between the devices themselves is what is the imperative thing here, okay? If you know you have a baseband module, and you know you have a microcontroller module, they have to talk to each other somehow. And the most common way that they do that is over serial. Standard serial port, right? Like we all know, DB9 serial port, standard RS-232, very simple stuff. So, if we know that they are using UART, the only other thing we have to care about is whether or not we can sniff that bus, or if it's encrypted, right? But if you remember that these things are so inefficient, there's probably no way that we can do that and have to worry about encryption, right? So the biggest issue we're going to have to deal with is whether or not there's SSL or PKI used between the baseband processor itself and the actual cellular network. And in a lot of cases, we never have to worry about that either. So, very quickly, we'll go over the processes, and you'll start to recognize the patterns that you're very familiar with in everyday computing applications. So here are some examples of actual network requests between a microcontroller and a baseband, right? Here we go. At the very top, what do you see? HTTP, right? This is a command to issue HTTP messages through the baseband as a client. Very standard stuff, right? The second one is actually a command that stands for setup socket. This is a standard Unix socket command, right? So the baseband over serial is actually implementing common Unix commands that we recognize. The next one is even UDP socket receive from, right? Very simple API here. And of course, we also have the incoming and outgoing SMS, because that's another primary channel, right? Your data channel or the network connection is going to be the #1 way that you connect to internet services. But SMS is also worldwide as well, right? So we may send or receive messages over SMS too. That M2M is called a shoulder tap. It's mostly used when devices are in sleep mode. So if I have an ATM and nobody's using my ATM machine, it'll power down, go into sleep mode. But if somebody needs to pull it remotely, it'll actually receive an SMS over the cellular network, and that wakes up the processor, and it says, oh, hey, I have an action to process. Is it a firmware update? Is it a command to upload statistics, etc.? And it'll come out of sleep mode, do its processing, then go back to sleep if it needs to. So if the payload is encrypted, it's very important to note that there are only so many ways it can be encrypted, okay? And that's often, one thing I didn't put up here is GPS coordinates. GPS coordinates, if you know that a ATM machine is always going to be in the exact same spot, and you don't want that ATM machine to be moved, it might actually take GPS coordinates and use those to derive a secret key, okay? And it can get that from the baseband chip. Also, the IMSI or private identity subscriber value that's in the SIM card can be used to initialize a key, okay? GSM timestamp can be used if you're developing a nonce, something of that nature. There are other examples there, but essentially, all these values you can retrieve. You can either retrieve them from the SIM card, or you can retrieve them from the actual device itself, because these basebands have to be approved by some kind of entity like the FCC. And these entity organizations require you to write down the IMEI and other values on the packaging, okay? Which means if you're walking up to one of these systems and you can get access to, you know, the part where it actually has the baseband inside, you can write down, oh, the IMEI is XYZ without ever having to break into the device, which is great. But it's very important to know that because M2M is so lazy, most people never encrypt, all right? But if things are encrypted, or just generally we need to reverse engineer the protocol, how do we do that, right? It's a very simple process, and we just use data sheets, right? This is a very, very simple thing, right? This is common first day stuff for reverse engineering. I'm sure you guys already know it, but this is the easiest way to break M2M. All you have to do is say, hey, I want to hack an ATM. Okay, let's look up forums and see what forums have been has this ATM manufacturer been visiting. Maybe it's ARM32 forums, maybe it's ABR forums, right? But those forums are going to talk about, hey, we need more help developing this specific chip, kind of ADC processing, or power, I come out of a sleep mode and I'm in a weird state. How do I deal with that? And once you actually see those problems in forums, you can identify, wow, it looks like a lot of these guys are using Atmel AVRs with 8-bit microprocessors. Download, the more commonalities you see between the same chips on that architecture. And you get to know very quickly, wow, these particular processors implemented by this vendor don't have any security capability whatsoever, right? And in a lot of cases, buffer overflows, it's like Windows 95 all over again. It's that easy to implement a remote code execution vulnerability on these kinds of what kind of chip it is, and don't actually have access to the specs, or you can't get the information, or you have a copy of the device, a version of the device, maybe even a demo, and you break it open and there's no marking on the outside of the chip. It's still very easy to find the pins that you need to know. Because remember, the only communication that the microprocessor has to the world is over serial between the microprocessor and the baseband. That is the only way it can talk. So the easiest thing that you can do is just take a multimeter, right, and trace the connections between the pins on the baseband and the pins on the microcontroller. You'll find 4. Power, ground, receive, transmit. That's it. That's all that's needed. And once you identify those 4, it's extremely easy to drop off power and ground, right? You're not going to see any traffic there. So you hook up a logic analyzer, next thing you know, you're intercepting traffic between receive and transmit. That's all you have to do. Super easy to identify those. So, as I said, logic analyzer, the async for all these serial boards, it's standard 9600A1N, right? And the other mode is 115.200. And those are the only serial standards used in communications between basebands, because basebands are basically developed with the standard to either use one of these two speeds. And that is it. Those are the only speeds. And this is just a simple example of a chip that I reverse engineered using a logic analyzer. And you can see the hex across the top. It's kind of small, but you might be able to see those hexadecimal values. But it's essentially what, like C36-GD, right? So that's ASCII. Very easy to sniff, not encrypted, just straight up ASCII. And this is an example of information that's passed back and forth between a microcontroller to the baseband. This is a device that I reverse engineered that was a GPS tracking device. Okay? Law enforcement uses this. People use this to track their kids, their pets, their valuables. In the United States, this module specifically is also used to track valuables as they're trafficked in trucks across the United States, so for shipping. And I reverse engineered this device, and this is the information that was dumped between the microcontroller and the baseband. So I could actually see some very important things here, and I'll talk about them in depth later. But see, what's that? TCP/IP connection requests at a specific IP import. It's that easy to find information on these devices because M2M is so inefficient. Attacking, as opposed to all the crazy, new technologies we could be attacking. It's time to actually start reversing, right? We know the methodology, we know what things our target is going to be using, and now we just attack those things. So it's sometimes difficult to guess crypto keys, but like I said, most of those values are easy to guess, or they're embedded right in the firmware. You can usually download the firmware. There are some simple ways why. I don't know if a lot of people here are familiar with hardware hacking, but hardware hacking is a lot easier than you think, right? If I can do it, everybody in here can do it. as well, right? I am not that slick, but some people are, and that's like Travis Goodspeed and the guys at Cryptographic Incorporated, Josh Wright, and these guys have all developed techniques, glitching, simple power analysis, differential power analysis, etc., that all help you gain information from a microprocessor, okay? The most important of these is glitching and differential power analysis. And the reason why is because essentially what occurs is every single time a processor, whether it's a robust CPU in our laptops, our phones, or a microprocessor, every time it needs to perform a cryptographic operation, there's a spike in CPU usage, right? Because there's a lot of mathematics and important algorithms that are used in the processing of cryptographic messages. So a normal power spike is seen during that time. Well, you can actually read the emanations in RF from a chip when it's in those states. And you can determine whether or not it's an XOR operation or an AND operation or some kind of other significant operation based on the power that's used in the CPU at that particular time. And if you have one of those CPUs, you can actually implement your own code to measure statistically, okay, let's iterate over a while loop and process an XOR command over and over and over and over. And you sample the power to determine the level of power that's used every time that command is executed by the CPU. And you'll notice patterns. And you can actually differentiate between an XOR and an AND, an addition, subtraction over time. So you'll be able to figure out when it's performing these specific operations, how it's performing those operations, and when you're going to be able to see it pull information from memory, right? And sometimes the longer the operation, the larger the number. So you'll actually be able to derive what the specific numbers are that are being processed by the CPU. That's a very important technique. The second technique is glitching, which Travis Goodspeed got very, very well defined in his GoodFet. A small little board that he developed to hardware hacking, and it implements glitching. And what glitching does is it adjusts the power level over time. The board that you're using, unblown, it's set at 1. It's either true or false, like any other bit, right? But with power, because it's all based in power, it doesn't know whether that bit is set or not if you mess with the power levels. So if you trick it into thinking that it can read a specific fuse at a specific time and then drop the levels at the same time that it's trying to read that fuse, you'll trick it into believing it's either a 1 when it's a 0 or vice versa, or it's 0 when it's a 1. And those fuses determine whether or not the security can be bypassed. If security can be bypassed, you can then download the firmware image that's stored on that microprocessor, which people do not want you to have, right? Because then you just basically have your source code, right? We're all reverse engineers. We know that having the binary means pretty much having the code. And that's why those fuses are designed, so that manufacturers can lock their code so people can't steal it. If you use glitching, you download the firmware by tricking the CPU into thinking you are allowed to, and then you reverse engineer that firmware. And most of the time, inside the firmware, you'll just see static keys, right? You may even have two fields. One field that says secret, and the next field that's the actual password. It's really that easy, right? So, as I said, reverse engineering a CPU, a microprocessor, is extremely efficient because it's not that time consuming. In fact, I want to show a quick example. I'll go through this. I have a lot more to get through. But the STM8 is found on many, many different types of M2M systems. This is a very ubiquitous chip. Okay? What's great about this chip is it has only 96 instructions and a small amount of memory, which means you can reverse engineer any flash on it very, very quick because there's not much that it can do. Right? So here is a disassembler that I wrote since there were no tools. Can you guys see that okay? Is that too small? Yeah? Okay. So I actually used glitching to pull this firmware off of a board that I was attacking. And just dumped, I wrote my own disassembler because there wasn't one available. The IDA, if you guys know IDA for reverse engineering, it only handles STM7 architected by ST Microelectronics. which is, I believe, their 32-bit version. But STM8 doesn't map directly into STM7, so I had to write my own disassembler. But anyway, this is the interrupt vectors for this specific firmware image. And what you'll notice is this. This is actually live code, right? But check this out. If you guys can see the addresses, what are the addresses here? 8080, 8080, 8080, 8080. Every single vector here is 8080 for its address, except for 3. The reset and UART transmit, UART receive for serial. So this again proves that the only time that we need to care about what the microprocessor is doing is when it's interacting over serial to the baseband and its actual application, which is the reset vector, right? So that means it's extremely simple to reverse engineer. And to prove it, I mean, this 8080 could be, you know, a function that processes many different things. But you'll see that's not the case, because when I wrote my disassembler, I proved that if I go to address 80, address 8000 maps to address 0. So when you go to address 80, it's really 8080. Regardless, you'll see the only instruction there is IREP, or return from interrupt, meaning don't process this, right? So every single other function of this microprocessor is not used. So that means there's a very small amount of code that we need to reverse engineer. And it's even smaller when we start looking at this interrupt. This interrupt vector is for the serial receive function. 2 instructions. Not hard to reverse engineer, right? All it does is it retrieves the value from the address 5231. And we'll see in the manual for this chip, address 5231, your data receive is the data register, where the byte that's read from serial is stored. Okay? So all it's doing is receiving that value from memory, storing it in the accumulator, and then returning it. That's all it does. Simplest function to reverse engineer ever, right? That means that the rest of it is all just in the reset function, and that's probably a very simple amount of code to reverse engineer. Won't take too long, right? So this instruction architecture is pretty simple. I even wrote an emulator because it was really, literally that easy. And you can see, like, it's pretty straightforward. I just had an emulator that actually stepped through functions so I could see how it was processing each instruction, what was occurring afterwards. So I could see when it's actually building up a buffer and building out secure keys. This was an interesting case. This firmware image here would store bits and pieces of the secret key around in flash memory. So I was trying to be smart, but we figured, okay, what I can do is I can emulate this firmware image, and I can run it through the process, and when it builds up something that looks like it's pulling pieces of memory from random parts of the firmware image, I notice when that occurs, and I stop and I read that value. And that turned out to be the secret key. So, point of reverse engineering is for 3 main reasons, okay? You check SMS, you determine whether or not SMS messages are being processed coming in, you determine whether or not it's going out to the internet, what those messages are, and what they look like, right? And you determine whether or not it's receiving or capable of receiving voice calls. So, the communication channel, very simple. We're running on 10 minutes, so I'm going to start skipping through some of this because this is all a little bit academic and I want to get to the fun stuff. So, we'll talk about building a fingerprint real quick, because once you understand the way that these devices connect to the network, you can start looking for them all over the telephone network. And that's where things get really fun, right? Because what occurs on the telephone network, every single time one of these devices gets allocated, it's given a specific phone number. 1, 2, 3, 4, or whatever, right? Well, the network allocates numbers to these specific devices in either pools or random slots. It's one of the two, depending on the carrier. AT&T is very well known for allocating numbers in chunks. T-Mobile is very well known for allocating numbers randomly. So you'll be able to develop a fingerprint to say, oh, I'm attacking an ATM system. And the ATM system is internet connected. But it's internet connected over the cellular networks, which means that it receives a phone number. And I know that it's only, they're partnering, say, with AT&T. So every time I scan a phone number, if the HLR information tells me that this phone number is an AT&T phone number, there you go, right? It's an AT&T phone number.
The caller ID is always associated with the manufacturer, say Scott's ATMs. So every time that I pull caller ID information for a phone number, if it's Scott's ATM, that's probably an ATM machine if it's on the AT&T network, right? Very simple techniques for developing a profile that allows you to scan millions of phone numbers for one specific set of information that you're looking for. And the point of this is to develop over time a methodology for finding phone numbers that you can send SMS messages to, right? Because, again, like I said earlier with the shoulder tab messages, SMS is usually a major control channel, okay? So, since we're running out of time, I'm going to skip some of this stuff, but this is an example of pulling information on a particular phone number. So I just picked any random phone number, okay? 310016 is in the United States. This represents the Cricket cellular network in the USA, okay? So I know precisely what network it's on, and then I pull a caller ID name lookup, reverse engineer the name, and determine that the person that owns this phone is named Virginia, last name bleeped, but it doesn't matter. The point is you get her name, okay? And you can scan millions of phone numbers for this information, build a fingerprint and say, I know this is likely to be the device that I'm targeting. Another really quick example is the AT&T iPad. So Apple and AT&T partnered in the United States to ship the iPad. And you can scan phone numbers for it. And the fingerprint is this. The provider is always AT&T, which is 310-410 in the United States. The caller ID is always the billable name, so you'll always receive a person's name instead of industry, right? And then you'll always determine that the location or the mobile switching center number is never in the same location as the phone number's registered exchange, right? So in the US, if you have an exchange of 310, then that means that you're likely to be in Detroit, Michigan, right? So then again, you can also call the phone number and determine if it's capable of retrieving voice. A lot of cases with M2M, it will give you an error and say, I'm sorry, this phone number cannot be called. If you know that it can be called, but it's allocated to a human, it's a machine, right? And this specific fingerprint can be used to find iPads all over the world. So, that's a lot of stuff to go through. So what we're going to do is we're going to look at the case study real quick. This is the tracking device that I reverse engineered. I'll just go through it very quickly by showing you the highlights. Let's go back to this stuff that I sniffed over the logic analyzer, okay? We saw the TCP IP address, the IP, the socket, we connected to it, and this is an HTTP push. As you can see, this actually has, I've exited out here, but this is the phone number for the device that was actually uploading information. So I know what the phone number is, okay? I also know the time, I have the timestamp, and I also have the location area code and carrier identification, excuse me, for the specific cell towers that are around this tracking device. So this tracking device is a GPS or assisted GPS. What occurs is, if GPS cannot be retrieved because of cloud, overhead, blockage, etc., it retrieves the caller, or the cell tower identification for all cell towers around it, right? And that information can be used for triangulation. So that is the assisted GPS. And what's very interesting is that there's an SMS payload that's used as the command channel for this M2M device. So every time it needs to, every time you request a location of this tracking device, an SMS message is sent to it. And here's the example here next. So what you may notice is there's a lot of junk here. There's most importantly a lot of zeros, right? Well, there's this one blob, 43CAED70, that just seemed out of place with the rest of the data. What it turned out to be is an IP address. And the IP address, of course, is the name Zoomback, right? So Zoomback LLC, the manufacturer of this device, actually registered an IP network, and then IP address is part of this network, and they put it in the SMS. What does that mean? A, connect to this specific IP address and upload your GPS data, right? So what happens if I write a script that scans through the entire cell phone network sending these SMS? This is what happens. I get every single GPS tracking device in the world that's made by this manufacturer to connect to me and upload its data to me. Not only that, but it uploads its phone number so I can connect to it later. What's even better about this is it bypasses the entire manufacturer's network, so they have no idea that I'm doing this. So I'm essentially stealthily tracking everyone with the GPS in the entire world. And this is me. This is the location. This is my car. Well, this is actually not my car, but this is the parking spot where my car was when I attacked my own GPS device. So you can see it working. The second case study, and I'll show you, is very quick. I'm sorry for taking too much time. But we hacked a car security module. Myself and my partner in crime, so to speak, Matt Solman. He's also a researcher at ISEC Partners. And we decided to hack into a car. And the idea was we want to hack into a car, unlock the doors, start the engine, and drive off with it. And we succeeded. So I will show you a video real quick that demonstrates that. And hopefully you guys can hear it. But we'll see if the audio is any good. Can you guys hear? So what we're doing now is we're sending an SMS message via my laptop to the car telling it to unlock its doors. Now we're sending the second message which tells it to ignite the engine to let it start off. So we should start that. It'll take a second. So there you go. So this is the result, or the conclusion. As we already knew, embedded security is quite hard. Okay? You just can't get it right very easily. And there are really important things that we have to do to not make it hard, or to not make it easy for other people to exploit. Number one thing that we learn about this: do not embed IP addresses in your SMS messages. That's just not good. There are a couple other things too. Always use PKI SSL, etc. But there are problems, and briefly, if I have a moment. Do I have a moment? Okay, I have just a moment. So Centurion is doing an exceptional job of pushing the industry forward, but even they are having trouble, right? They're probably the best in M2M today, but there are a lot of issues that they have, and these are radio link stability, MIM. These are two extremely important technologies that they are pushing forward, but they have weaknesses on their own. RLS itself is to detect GPS and GSM jamming, okay? And that's basically like if I have an MC catcher, nano BTS, or some other technology that can force your device to connect to my cell phone network, it's supposed to be able to allow the M2M device to detect it. But there are serious problems with that. GSM jamming detection is very glossy. It's very troublesome, and it's full of false positives. So you essentially are only detecting if the downlink is being jammed as well. In some baseband modules, they are not capable of jumping channels. So what occurs is that if the uplink channel is a single channel, then you can jam the uplink, and that'll force it to try to associate with a different downlink, because it can't tell the difference. So downlink attacks are not the entire problem. Uplink attacks are also a problem as well. And also GPS is a really important example here, right? Because we have a satellite in space that transmits at 30 watts of power. but it's also 20,000 kilometers away. So by the time it gets to us, the signal is about negative 120 decibels. That's way worse than any Wi-Fi signal any of us would ever want, right? Which means it's extremely easy to jam. You can jam GPS with your monitor, right? It's that bad. So if you look at it in that perspective, we can take the example of Moss Landing Harbor in San Francisco. There was a preamp that was used for a TV television receiver on a boat in a harbor. And this one preamplifier was so poorly designed that it jammed GPS for the entire harbor in a diameter of 1 kilometer. That's how bad it was. But what's important to learn from this is that GPS jamming is so simplistic and easy, and GSM is not far behind, that radio RLS is essentially a weak technology implemented to try to detect attacks that are extremely inefficient to detect, right? So there are so many false positives, it's just not going to be a profitable venture, and it's going to give you a false sense of security. Additionally, it's also important to note that UMTS active IMSI catching is going to be possible in August when Range Network implement their own UMTS stack for their OpenVTS software. That's going to be out in August. When that occurs, not only can we attack over 3G, we can also attack over 2G like we can currently, but you won't know the difference. If I don't have to jam other GSM signals to get you to connect to my network. If I have 3G capability, I just set my base station next to your device, and it thinks that I'm the network. There's no jamming involved. It's just like, oh, this is the best signal, I'm going to connect to that. That's it. No jamming needed, right? So the other issue is machine identification modules. These are brilliant little devices. It's basically a SIM, but it's soldered onto the PCB. Now, of course, we all know that soldering something does not make it safe, right? But it does make it trusted in most engineers' perspectives. And this is a serious problem because now we have a device that's soldered onto a board that interacts over serial communications, and now it's considered to be trusted because it's a soldered part of the board that can't be moved. Well, if we desolder it, and then we put our own in there, now that's presumably trusted too, right? That's a serious issue. And these kinds of issues are being discussed at Centurion and other companies, but I think that they're still a long way off before these modules can be used in trusted or secure environments, especially SCADA. Right? So there will be attacks, but the most important thing is SSL. And even if you use SSL, it's important to note baseband modules implemented for M2M, only 9% of available baseband modules today even support SSL and PKI. And even the ones that do, there's no security store. So the certificate authorities, where are they? They're not in the baseband. Are you storing them in your microprocessor application? No way. It takes too much space, right? Meaning, null prefix attacks, invalid CA attacks, invalid domain attacks, all the juicy things that we know in SSL are valid, still valid here, and easier here, right? So, thank you so much to NoCon team, and thanks to everybody, especially Alex Stamos, NCC, the EFF, and Joe Gratz, my lawyer, who kept me out of jail with the car hack, and everybody else that helped me there today. So, thanks so much for your time, I appreciate it, and let me know if you have any questions. Do we have time now? No. I'll be around all day. If you guys have questions, please do come up to me and we'll shake hands and talk, okay? Thanks a lot for your time.